I'm going to give you a bit of an overview of section 9.8. 9.8 is really about using the Pythagorean Theorem and some of our other right triangle relationships within three-dimensional solids. And most of the terminology is in the book. If you look at the examples, I think you can really figure it out. But for those of you who prefer to see these things on video and see what I would tell you in class, here you go. So we're going to be working a little bit with pyramids, and we'll talk more about what pyramids are in the future, but basically pyramids have a base shape, and they're named off the base shape. So the base of this pyramid is a square. We would call this a square pyramid. If it was a pentagon base, you could call it a pentagonal prism. If it was a triangle base, you could call it, a pentagonal pyramid. If it was a triangle base, you could call it a triangular pyramid. So this is the base of the pyramid. A lot of times this is called the vertex of the pyramid, that top point. Some books will call that top point an apex. I don't think our book uses that term though. Faces. Faces are your flat solids. So you have a triangular face here. You have a triangular face here. The base is a square face, okay? They're the flat surfaces of your three-dimensional solid, okay? Edges are basically just the line segments that make up the shape. So we've got a 10-unit edge here. We've got an edge here. We've got an edge there. Any two vertices that are connected, that would give you an edge. The altitude of this pyramid is going to go from the vertex point, should go to the center of the base like that at a perpendicular. For example, if you're making a tent or a teepee or something like that, it's where that post would go that you kind of build the whole thing around, okay? So it will always be perpendicular to the plane of the base. And hopefully we know a little bit about lines being perpendicular to planes. They're perpendicular to all lines in the plane that pass through the foot. And then there's something called the slant height. I want to talk about the idea of the slant height here. For those of you who are looking at this saying, well, how does the Pythagorean theorem come into play in this problem? Here's the key. Let's say that I wanted to find the surface area. Okay, that's not actually the focus in this section, but the surface area. If I was going to find the area of the surfaces, like if I was going to paint this pyramid, I would need to know the area of each of the triangular faces that goes around this thing. Okay, so I could draw one of those triangular faces separately, okay? It's a triangle. We know that one of the faces has a base length of 10. The problem is when you find the area of a triangle, you need to take half the base times the height. And although we know the base is 10, we don't know what the height of the face is. And be careful, don't assume that this is an equilateral triangle or that it's a 30, 60, 90, two 30, 60, 90s or something like that, okay? If you don't have angle measures and you don't have anything that tells you angle measures, you can't make those kinds of assumptions, okay? So here's the key. The altitude of one of these triangular faces, if I drew it in the diagram, this face here would be leaning right here, right? So the height of that triangle would actually be leaning. It would look something kind of like that. And it's what is often referred to as the slant height, okay? It's a height. It's a height of the face. But since that face is leaning, it's a height of a shape that is leaning. It's slanted. And that's why it's called the slant height, okay? A lot of times, I don't know why this is, but a lot of times they abbreviate the slant height with an L, okay? I think we're just running out of letters at this point. So that's the idea, all right? So let's say that I told you that the altitude of this thing was 12 units, okay? And the base was a 10 by 10, and I wanted to find the area of one of the triangular faces, which means I need the slant height, okay? How do you find the slant height? Well, this section is a right triangle section. We are going to continue to use right triangles, and here's how. And hopefully you've been kind of conditioned to look for right triangles inside shapes. I can draw this segment right there, and that's a right triangle. Hopefully you can see that in purple, okay? I know one leg is 12. This is a square base, so that base has a length of 10. If you notice, this goes to the center of the base, so that length there is 5, okay? And you can either use the Pythagorean theorem here, so 5 squared plus 12 squared, then take the square root, or hopefully you recognize this is a little 5, 12, 13 triangle, okay? The height of one of those triangular faces was 13, okay? So now I can take half the base of 10 times the height of 13, and I think I get 65 square units for one of those faces. If I wanted the area of all the sides, I could take that 65 and multiply by 4, and that would add up all 4 triangular faces. If I wanted the total surface area, the area of all of the flat surfaces, I could add in that square base, which has a 100 square unit area. They're not really going to ask you to do that in this section, but that's why that terminology is so important. Okay, you'll see this within other shapes as well. So just to mention those other shapes. So let's say that I was working with a cone, for example. A cone, of course, has a circular base. And let's say that they told you that the base area was, well, let's say 144 pi. And maybe they tell you that the slant height is 20. And they want the altitude, something like that. Okay? Same kind of thing. If the base area is 144 pi, we know the area of a circle is pi times the radius squared. So this would tell us that the radius here was 12, right? Because 12 squared is 144. Okay? So you can put in the radius strategically here. Put in a 12 right there. Okay? The altitude goes to the top of the shape there. I didn't draw that real well, but the altitude is going to go to the top of the shape there at a right angle. It's going to be, oh, we don't know the altitude. That's what we're looking for. Call it A. This length here is 20, okay? And so again, you can see we've got a little right triangle here. It is a 12A 20. And I would always check and see if it's a triple. 4 divides into both of these. 4 goes into 12 3 times. 4 goes into 20 5 times. Okay, this little 3, 4, 5 triangle, they got multiplied by 4. So that missing side is going to be 16. Or you could use the Pythagorean Theorem. You could do a squared plus 12 squared equals 20 squared, and you could solve. But be on the lookout for triples. They make your life so much easier. So anyway, this time we used the slant height here, and we found out the altitude was 16. And in the surface area and volume chapter, those measurements are going to be really, really important. So look for right triangles within 3-dimensional shapes. It will make your life much easier.